Hello, hello, hello. I'm Mark. This is Oliver. Hello. He said hello. So this is we both co-maintain KVM on arm64. So unsurprisingly, we're really interested by Suzuki's talk about the CC architecture because we have our own take on that architecture. The title more or less sells it. So going to go very quickly through the first slide because you've been bored to death with confidential computing stuff. So this is what confidential computing is supposed to give you. Basically, you don't leak data. You can't infer data. Your data is safe. Software is able to verify that the platform has these properties. That's attestation, usually. And overall, what is not guaranteed is availability. You don't know whether you're going to be scheduled or not, but that's denial of service. In general, nobody cries too much about that. So arm64 is really made of a bunch of blocks. So you have the RME, Realm Management Extension, which Suzuki has detailed in great length. So it's a new security domain on the side. It's parallel to the two existing ones. You get some memory encryption. Recently, ARM has added per realm encryption. You get this fancy new third stage that basically is an additional permission check called granular protection check to enforce protection at a 4K basis. And it's exclusively managed by EL3, or now called root. And then you get the RMM, which is the Realm Management Monitor. And basically, it's some kind of proto-hypervisor, but not quite, specially designed to run confidential VM. And that coordinates with GPC to ensure isolation. So really, RME and RMM, that are the bits we're really keen on looking at. So this is basically another take on the drawings that Suzuki presented before. We should have merged these two presentations. So that's where we normally run them. So NS Hype is where KVM is normally, more or less merged with the operating system. And we have the VM on the side. At EL3, we have our firmware running, doing stuff. When you have secure mode on the side, well, you can have a secure hypervisor or secure partition manager, giving you some sort of trusted execution environment or secure partitions. The nice part is that secure has full control over non-secure, can happily spy your data. It's really good. And when you add the RMM and RME, then you can run realms. And the VM you were running in non-secure actually, it's not quite there. It's actually moved to the realm side. And EL3 has been keenly demoted to root. So it's still super privileged, but it's now its own world. What GPC ensures is that secure now cannot go and pick at the realm data. That's really the real innovation in this architecture. Well, for ARM. So what can RME do for you? Well, it gives you this split isolation model. You get GPC assigning, more or less assigning 4K physical blocks to a given security domain. And then you get your standard nested page tables to perform isolation within a realm mode. So when you run a VM in realm mode, we still have the same primitive to isolate them. It's your stage 2 page tables. And it's a split responsibility model. GPC, these tables are controlled by root, aka EL3. And the realm stage 2 controlled by the RMM running at realm EL2. So the software model is split as well. So we have some firmware running in root that is controlling this GPC. And then the RMM, as again Suzuki explained, is in charge of the guest state, the stage 2 page table management, handling of some, if not most traps, hypercalls from guests, and basically, well, anything that is related to CPU virtualization. The non-secure hypervisor that lives on the side, aka KVM, is providing memory. It's in charge of vCPU scheduling, basically user space management, and for now, interrupts. So, so the RMM interacts with the non-secure hypervisor, and you can create a RAM, provide memory, the payload. You can execute it, and then you can shoot it in the head and start another one. All that is done using SMC cores to ER3 that are then relayed down to the RMM. For the guests, well, it's fairly similar. You get RAM Service Interface, RSI, it's a bad acronym, which allows guests to get an attestation report, as we've heard before. It's quite important. Manage the sharing of memory on the non-secure side. If you want to share back some memory, well, you would use one of these services. And also details like, allowing booting virtual CPUs. So we use PSA for that. And again, this is another set of secure calls, or maybe HVCs actually, handled by the RMM and potentially forwarded all the way back to the non-secure hypervisor. So it's quite nice. I mean, that's what we've done for PKVM. It's actually extremely similar, except that.
Maybe a few problems. So first and foremost, looking at the ecosystem, ARM's providing a reference implementation for the RMM. We can all go look it up and read it and everything, but there's no guarantee that the systems that we're actually running on are using anything that looks in any way similar to the reference RMM. Vendors are free to squeeze whatever they want into there, and it's deployed as system software. So it comes as a package with your firmware on your system. So there's no assurance around the correctness of it. We have no idea what bugs might lie in there. We have no idea when those bugs might be fixed. So it's really hard for us to make sense of whether or not we trust it in terms of KVM handing off its VMs to firmware. And to make matters worse, there's no way to even update it right now with the current spec. So you're pretty much stuck with whatever EL3 is given to you. The API around it, so there's two interfaces, right? The RSI and then the RMI, which is the realm management interface, KVM talking to the RMM. That's a rather baked API, and it's done mostly in the interest of a certain hypothetical hypervisor that we won't mention here. And the problem that we have with it is it doesn't build good primitives for doing virtualization. In fact, it actually builds in policy in terms of protection, and it doesn't give us the fundamental building blocks that we really care about. So we don't really get to play with the underlying hardware, and we're stuck talking through a firmware interface to whatever sits on the other side. So, and why is it that we have such a bad feeling about this being a firmware interface? Well, firmware has a pretty colorful history on ARM. It does on many platforms, but ARM in particular, we have our good friend TrustZone that has provided us a lot of interesting quirks and bugs, and of course, vendors wanting to cram DRM and all kinds of fun things on the secure side. Of course, other people have taken issue with this. Android is moving in a different direction. That's why PKVM exists, to move confidential workloads out of that super privileged space. A lot of the problems with this is like the SoC vendors, they fork it, they hack it up, and we wind up with just this massive ecosystem of a whole bunch of different varieties, and there's no reason to believe that the RMM would be any different. So the vendors are also trying to squeeze in a lot of value adds into a secure world, like the DRM, like I was mentioning, and it's really difficult for the kernel to adhere to something that's architectural at that point. And then to focus on the problem of doing updates of those firmware implementations, there have been bugs. It's hard to review that because we don't get to look at the source, and sometimes you wind up with interesting issues in your firmware, such as this Qualcomm one that Mark reminded me of, where your GPRs just get overwritten every once in a while, which is fun. So, we're going into this thing with the promise of write once, run everywhere, but really this is becoming write once and debug everywhere. So we don't want to be in a model of a ship and forget business for our RMM. It's very uncomfortable to build a hypervisor around that. So does this really make sense for us, and can we really trust our VMs to such an entity? And to make matters worse, all of this is built around the moral platitude of zero trust. The idea is that the VM doesn't trust the hypervisor at all. But I would say that trust is a two-way street. From the perspective of the VM, right, they don't trust KVM, but from the perspective of the non-secure hypervisor, I just see this giant blob to which I'm handing off my VMs. So very unnerving there. And the CCA ecosystem was built largely in the interest of a reference hypervisor that may or may not be independently verifiable. There's possibly not going to be any source code available for your hypervisor, but we know that's in no way true for KVM. All of our sins and mistakes are on full display, proudly. This fact has actually been used as the basis for another virtualization TCB, i.e. PKVM. And there's been some success with it. So it really prompts the question of why do we, by definition, lose trust in something that has a proven 10-year track record that's also innovating in the direction of providing confidential compute and taking the belief instead that firmware will do it better. So it's, again, this mythical common API through which all hypervisors can interact with hardware. It's supposed to be good for everyone, but in reality, it prevents any sort of optimization between the RMM and your non-secure hypervisor. So looking at PKVM, the interface between the PKVM low visor and the kernel is flexible. You can change it and optimize it as you see fit. But instead, with the RMM, you wind up with getting very, very common interfaces. It's very much dumbed down to coarse-grained interfaces, and again, a lot of policy cooked in there too. And then the question becomes, what do we do when there's actually a bug in the interface, in the spec? If this happened in PKVM, we could just go and respin the low visor and come up with a new hypercall interface to fix our problem. But now it's in the hands of firmware, and it's not clear that we could ever get a change implemented in the API in a quick manner, because again, it's dependent on all of our vendors doing the right thing. So then the question becomes, in KVM, should we just outright revoke support for these implementations? That's not very good. It doesn't feel like a good stance for the ecosystem, right? Because we want to be able to run on available hardware. But we may not even have a choice in it, because carrying all of the baggage of the hundreds of errata, if you will, of all these implementations would just really bog down KVM. So looking at some of the track record with KVM and PKVM, so like I had mentioned, having an inflexible API between your TCB and your non-secure hypervisor really didn't work, and it allows for flexibility and innovation, both in terms of new feature support, but also to respond to security issues and just bugs in general. It's also really important for performance. We can be very deliberate about what state exists where, be it on the RMM side, well, excuse me, on the PKVM side, in the kernel, or perhaps even shared between both. But now, since we're narrowing things down to a singular API, it's not going to allow for such diversity with the hardware. We're stuck with a software model, even though we really want to be getting to the underlying hardware. And a lot of the problems with innovation is not only is, so it's mostly focused around the reference hypervisor, but we don't get to build interesting things for KVM. And it also gets in the way of development for other ecosystems as well, because it's not the case that we're going to be just doing secure virtualization the entire time. We support non-secure. We have a wide variety of use cases that we want to support in KVM. Next slide. So as sort of a case study of like the performance issues that we brought up, so like having a more flexible API between the RMM and the hypervisor. One example of this is handling the GIC. At least in the current architecture, all of the GIC emulation lives on the non-secure side. I mean, yes, it's quite a massive pile of code, and understandably, you don't. Well, maybe there's one, maybe two of you who like it. Anyway, so all of the GIC emulation lives over on the non-secure side. So that means pretty much any time that we need to do any interrupt handling, It has to go all the way over to the non-secure world. And this is normal for physical interrupts, right? You don't want RMM to be handling unrelated physical interrupts in the system. But it really gets in the way of us optimizing virtual interrupt injection. And one example of that is the EL1 timer. The EL1 timer is directly programmable by the guest, but we get physical interrupts that come out into the non-secure hypervisor. But theoretically, we could come up with a model where perhaps some of that GIC emulation state is shared between the RMM and the non-secure hypervisor. If the RMM was able to introspect and look at the GIC state, it could perhaps determine to go ahead and inject a virtual interrupt that was targeted to the guest without even doing a full exit and context switch back into the non-secure world.
I'll take over. So what's interesting is that it seems to go into, at least on the ARM side, seems to go in the wrong direction. I mean, currently the direction of travel was that we're trying to, especially with the PKVM effort, and yeah, full disclosure, I've been involved with that, so I deeply care about it. We're trying to remove a lot of things from running in secure world, to bring that into VMs, and to break basically the correlation between being confidential and being privileged. And it is a change that we really need on Android, because people tend to run all kind of crazy stuff on the secure side. And we can do that without binary blobs that cannot be replaced. So there are some good properties. We can ensure that the payloads are confidential, but the hypervisor, everybody can run it, can hack it, hack it in sense, modify it, improve on it, and eventually ship it. And if you look at how the architecture works, it wouldn't be hard to take the non-secure EL2 side of PKVM, what people call the low visor, and move that as the RMM. The architecture actually lends itself really well to that sort of transformation. And we would have a fully self-contained, realm-capable hypervisor, where you can upgrade everything in lockstep, where you can have some degree of flexibility between non-secure and realm, and reap the performance that there are a lot of low-hanging fruits there that we could benefit from. But yet the CC architecture actively prevents this with the RMM. And it's really a bit annoying. CCA really reuses, and Oliver said abuse, the existing ecosystem, and it really begs the question: what do we do now when we get features that cannot be implemented with the current CC architecture because of limitations of the RMM? Do we drop the feature on the floor, or do we say that no, well, sorry, RMM prevents us from doing so, so we're just, there'll be one loser in the end. It's not very good. I'm personally extremely concerned about the amount of platform-specific workarounds that we're inevitably going to have because of this model of forking existing firmware and vendors having all sorts of quirks on their platforms. These quirks are going to trickle down into KVM. From a maintenance perspective, it's not a good prospect. And frankly, it also means that we get a KVM implementation that becomes increasingly fragmented, siloed. So yeah, you can read. It's a rant, I agree, but enough ranting. That's the Italian speaking. So what do we need really? So if we want to make CCA really a first-class KVM implementation, well, we need an architected and secure way to deploy an RMM, and at boot time, and an RMM that will be provided by the hypervisor itself. I mean, subject to all the possible restrictions you want, signing, secure boot exists for a reason, that should be part of it. So it has to be architected because we don't want, 36 or more different methods of doing so, and we want it to be verified, secure, attested, whatever. We're talking about attestation. We want an architectural way to measure that the RMM is actually what we think it is, and we want that to be independent of the RMM implementation. And we want to be able to leverage the secure boot infrastructures that exist. And there's a plural here because EFI and Android have clearly very different requirements. They work in a very different way, but we have also a very diverse ecosystem, and I don't think it should be the architecture to decide which ecosystem is more important than the other. And yeah, as we're now getting with QEMU some open source implementations, it'd be really good to have that quickly enough. So does it mean it's a wasted effort? Absolutely not. So the hardware architecture first is perfectly sensible. I mean, it maps really well onto the current principles of the architecture, with exception levels and stuff. We absolutely can see how to make it work. Provides the right primitives. Okay, we still have this nagging feeling about the GPC being handled by ER3 root, but there's no policy there normally. It should be be only behavior. Should be okay, hopefully. Even some of the RSI, so the RAM service interface, is probably good enough. I would love that to merge a bit with PKVM because they tend to overlap with different restrictions, but hey, that can be made to converge. Finally, even the RMM itself, I mean, it's open source. I haven't checked the license, but hopefully it's compatible with Linux itself. But it'd be good to be able to reuse some of the boilerplate code that exists there as a library and use it with other open source hypervisors. It's really the API we object to. So, had a quick look around. I know nothing about the other architectures, of course, so what do they do? So for x86, it's sort of simpler because there are only 2 vendors, and they're very much in control of what's happening there. So the microcode helps. We don't have that luxury on ARM. But it still suffers from being quite inflexible. So it's in a way, it's a similar problem. But at least the upgrade path is really well defined. I've had a look at RISC-V, and at least for the stuff that has been posted on the list, it sort of looks like the RMM, at least Cove in the HS mode, where you have some firmware running in M mode and some other variants I didn't quite follow. You get an API, so I wasn't sure how it was called, but there was a CoV and CoV-H. Apparently CoV got renamed to CoV-G. Don't know why, no idea. So, well, I think that's someone woke up. And for S390, I have no idea. Christian, you'll have to explain how that works. Oh, beer. Talking about that, almost. So here's a message to ARM. So CCA is really one of the major ARM v9 features, and it really has the potential of redefining how workloads are isolated and made confidential on ARM. And making sure that the use of these functionalities, the use of the architecture really is not restricted. That's really essential. I mean, that's how the ARM architecture managed to get off the ground. And it has to be said, KVM has been really an enabler for ARM in the ecosystem, and we, especially in the data center. And we'd like to ensure that this trend continues, and we'd like to be able to carry on innovating in that field. So what we ask ARM is to give us the tools to basically meet this ambition. And that's it. Thank you. There are questions?